Good afternoon, everybody. Let's get started with the class. A couple of announcements. First, starting from this week, Monday and Wednesday at 1 p.m., we are going to meet for the project that we are going to be working on, as well as do a little bit of statistical programming and some project-related stuff. That's one thing. Monday and Wednesday, we are going to meet for 1 hour. The same Zoom link, okay? The same Zoom link. And also, you don't have to attend both of these days, even though I prefer that you do. I'm going to be covering the same topics on both days, all right? But I kind of encourage people to attend both of these sessions. It's going to be just 1 hour. I'm not going to take it more than an hour. The second announcement is that we are going to have our second midterm, which is going to be Monday, November 22nd, Monday. And November 22nd. Structurally is going to be the same, okay? Nothing different. Everything is the same. The topics that I'm going to cover are going to be from everything that I covered after the first midterm all the way up to this coming week, Wednesday, whatever I cover in between. Everything will be included in the midterm. And nothing to worry about the midterm. If you have been doing the homework and keeping up with the materials, you're good to go. All right. And also some of you maybe, I have been getting some emails about opening the homework. I tend to be very generous and helping. So I'll give you an opportunity to make up for the homework. I'll probably open some of the old homeworks this coming week so that you can work on it. I might even do it earlier, but I will send you an email if I do it earlier. If you missed anything, this is your opportunity to make up for the missed points, as well as it'll allow you to prepare for the midterm, okay? So that's all in terms of logistics. Now let's go ahead and start with the materials. Last time we talked about point estimates. Point estimate is an estimate from a sample. If you take a sample, from that sample, you can come up with some data points, such as if you take a sample of 200 students from Hartnell College, okay, and ask them how many hours they study, okay, how many hours they study per week, and the average of those 200 students, let's say, comes out to be 16.5 hours. Or let's make it a simple, nice number, 16 hours, okay, 16 hours. Now, there is a point estimate you got from the sample. Now, as I said previously, the objective of statistics is to kind of make conclusions about the population from the sample. So for instance, you took a sample of 200 students from Hartnell, and you found that they study 16 hours per week. Now, from this, you make the conclusion that, oh, okay, maybe average number of hours Hartnell College students study is somewhere around 16 hours. That's kind of the conclusion that you're making. So from sample, you go into predicting the population. So like this is X bar, right? The sample mean. From that, you're gonna make conclusions or make predictions about population mean. Or if you're talking about proportion, let's say you took a sample of 200 students, ask them whether they go to the gym or not, whether they go to the gym or not. So that would be a proportion question. So that gives you sample proportion as opposed to sample mean that we did here, okay? So from sample proportion, you want to make conclusions about or make predictions about, prediction is not the right word, conclusion, about population proportion, okay? We will be talking about predictive models such as linear regression coming up, okay? That's more like prediction. Linear regression, right? And then sample variance like S squared. From sample variance, you make conclusion about population variance, sigma squared. All right. So point estimate we talked about. Then point estimator is the formula that we use, and the parameter space. And the parameter space is the collection of all the points that the population parameter can take. Okay. The parameter space is the collection of all the points that the population parameter that you're trying to learn about may take. So for instance, if the number of hours a Hartnell student studies per day, the parameter space for that would be like from 0 to 24, because you cannot study less than 0 hours and you cannot study more than 24 hours in a day. If you're talking about proportions, your parameter space is going to be from 0% to 100%, right? Which is the same as from 0 to 1. So it is context dependent. Like, say, for instance, if you're talking about the height of a person, in theory, it could be 0, but an individual's height probably won't be less than 0. So let's say 0, all the way up to, I don't know. I don't think that there is anybody on the planet who is 8 feet tall. Anybody 8 feet tall? I haven't heard of any. So let's make it 9. So your population parameter can take on values anything between 0 and 9. So this parameter space, which is denoted by omega, is context dependent. Okay. Next, we're going to talk about point estimator. We did different formulas that we use, biased versus unbiased estimators. We know that we use X bar to estimate what? Mu, right? We use P hat, sample proportion, to estimate population proportion. We use S square, sample variance, to estimate population variance. As it turns out, these estimators, all of these are estimators, okay? These estimators are unbiased if expected value of X bars, all the X bars, the expected value of them is mu, then it is called unbiased. Or the expected value of P hat, expected value of P hat is P, then we'd call it unbiased estimator. P hat is an unbiased estimator of P. And expected value of S square is equal to sigma square. That means S square is an unbiased estimator of sigma square. So X bar is an unbiased estimator of mu, P hat is an unbiased estimator of P, S square is an unbiased estimator of sigma square. However, E of S, expected value of S, is actually not equal to sigma. So S by itself, instead of squaring it, is not an unbiased estimator of sigma. All right. In general, instead of using these symbols, they write an estimator theta hat is unbiased if expected value of theta hat is actually equal to theta. Theta is the population parameter, and theta hat is the estimator. Okay, theta is the population parameter that you are trying to estimate, and theta hat is the sample statistic or some estimator. And that is this. Now let's talk about confidence interval. This stuff, by the way, I already talked about it in this page, all the stuff. I talked about it in the last slide. And once again, there are some typos here. So please kind of clarify it, which I wrote down. E of x bar is equal to mu. E of p hat is equal to p, like here. And E of s square, like here. S square is equal to sigma square. And expected value of S is not equal to sigma. So these are the things I couldn't get the math symbols to be written properly on the PowerPoint. So those came out to be kind of as a mistake. So these are the things I want you to make sure that, you know, this is the real formulas. Any question, anybody so far about the materials that we talked about?
I don't have anything so far.
Thank you, Don. Anybody else?
No.
Okay. Confidence interval. I love to give this example in a very, very simple way. Okay, this sounds like very fancy. I talked about it yesterday, and I talked about it yesterday means Monday, and then I'm going to be talking about it again. So let's say Don, I asked him to go and, you know, survey a bunch of students, let's say 200 students at Hartnell College. Okay, so your sample size n is equal to 200. So go and Don, find randomly 200 students and ask them how many hours they study per day. Okay, so Don comes out and asks a bunch of people. All right, like that bunch of people is 200 people randomly selected. He asked those people and came up with 200 numbers and averaged those numbers. And he came up with, let's say, per day, X bar is equal to 3 hours, let's say. Okay. A student studies on the average 3 hours. So we want to find out on the average how many hours a student from Hartnell studies. All right. How many hours they are studying per day. However, we can't go out and ask 15,000 students that we have, right? And collect data. We don't have enough people or money to do that. So what do? We kind of take a sample that kind of represents the population of Hartnell students of 15,000, right? And find the average for that. Now, based on his calculation, Don says, yeah, this is the number I got, but this actual average for the Hartnell College students on the number of hours that they study per day is not more than likely it won't be 3 for sure. Okay, almost pretty much 99.99% chance that it won't be 3. It will be plus or minus some number, and that some number, let's call it 0.5. So Don comes out and says, you know, I did the average. I got like three hours from a sample of 200. But my best guess or best estimate, based on the data collection and my experience, it would be somewhere like this: 3 minus 0.5 or 3 plus 0.5. So that means he's saying that it could be as low as 2.5 or 3.5. So he's saying that, oh, okay, I think the actual average number of hours Hartnell students study, it will be between 2.5 and 3.5. And what he just did is created something called confidence interval. Confidence interval. Okay, and I asked Don, so you created this, Don, how confident are you? He says, oh, yeah, I'm 80% confident that that actual number of hours Hartnell students study falls between these two numbers. And that's like a layman's way of creating confidence interval, but it is very powerful. All the time, people are making these kind of inferences or these kind of conclusions in their lives. Like, I want to take a vacation. How much money I will need? Approximately, I'm guessing, let's say $500. So give or take $50. You're in essence creating confidence interval for the population of travelers that go to the destination that you're going to from your location. So you are in essence creating a confidence interval. And pretty much in everything well, not everything, probably many things in your life, you are creating confidence intervals subconsciously. And Don said like 80% confidence level, meaning that what it means is that I don't want to get into the technicality of it, but let's go ahead and say again in layman's term, it's like, okay, 80% confident, like 80% of the times probably I will be correct. Let's put it that way. 80% of the times Don will be correct. That's what it means. All right, give me a second. There are a couple of questions. Let me look at it. Okay. Where did the 0.5 come from? Dennis, that number I kind of made up, okay, this 0.5. Or Don made it up. So somehow, like, from his experience, he's just guessing that number. Now, I gave you this whole example just to get a feel for confidence interval. Now, of course, in statistics, confidence interval is done more rigorously through the use of something called central limit theorem. We talked about it, and because central limit theorem ensures the bell-shapedness or normality of a distribution. Once I know the shape of the distribution, I have more control over it. All right, let's see. Dennis has another question, I think. Dennis, what does it represent? It basically represents, so just think of it. You get an average of 3 hours students studying. You ask 200 students how many hours they study each, right? Then you got the average. The average is 3 hours. So from your guess, you're saying that, oh yeah, it could be a little bit more than 3 or a little bit less than 3. And that little bit more or less is 0.5. Okay, it's not 0.5, it could be 0.3, it could be 1, it could be some other number. Dennis, does it clarify your question? Great, thank you, Dennis. All right, so that's what a confidence interval is in ordinary man's language. Now, let me kind of make it sound more official. What is a confidence interval? A confidence interval for a population parameter. So for a population parameter, the confidence interval is an open interval of this form, like A, comma B, and on which we assign some confidence level. So like in case of Don's example, he said he has 80% confidence level, meaning that he's claiming 80% of the times probably he would be right if he were to do it many times, okay? And 20% of the times he may not be. 80% of the times he will be correct, and 20% of the times he won't be. And what does it mean in terms of actual definition? This is what it means. Let's say, again, Don took a sample of 200 students, right? And got average. Now, if he were to create samples like this For the first sample, he get an X1 bar. For the second sample, he get X2 bar. For the third sample, he gets X3 bar. And let's say he does 1,000 samples. So he'll get X1000 bar. For each of these samples, averages, he's gonna create a confidence interval like A1, B1, A2, B2, and A1000 and B1000. And 80% confidence level means that out of these 1,000 intervals that he has created based off of 1,000 different samples of size 200 each, okay, out of these intervals, 80% or 800 of them, 80% of 1,000 is 800. 800 of them will actually include the actual population parameter here. The population parameter in this case could be mean, it could be proportion, it could be a standard deviation / variance, okay? That's what it means. If it is 90% confidence level, that means 90% of these 1,000 or 900 of them will probably include the population parameter in question, and 100 of them will not. All right, that's what it means. Now let's move on. We talked about this. Confidence coefficient is the probability, and confidence level is the probability expressed in terms of percentage. All right, now how do you create confidence interval? Remember, this is where the central limit theorem comes into play. For sampling distribution for sample means, we had something like this, right? Sampling distribution for sample means, if you have n greater than or equal to 30, okay, n greater than or equal to 30, you have the sampling distribution, which has mu sub x bar is equal to mu, and sigma sub x bar is equal to sigma divided by square root of the sample size. And in that case, we know that the sampling distribution is bell-shaped. Now think of this, but this time, instead of sampling distribution for sample means, think of sampling distribution for sample proportions. It could be also bell-shaped, okay? Instead of using mu sub x bar, I'm gonna use mu sub p hat. P hat is the sample proportion, okay? And then sigma sub p hat. Sigma sub p hat, mu sub p hat, and sigma sub p hat. And these has a value. Mu sub p hat should be just p, and sigma sub p hat is square root of p hat times 1 minus p hat, all of it divided by the sample size n, I think. All right. And this thing, you can just briefly browse over this stuff in the course materials that I have provided. Now, this allows us, by the way, this allows us to use the central limit theorem conclusions for population proportion. Here, by the way, there is a condition as well like this, but in this case, it's NP is, I think, greater than or equal to 10, and NQ is greater than or equal to 10, where Q is nothing but 1 minus P. So these conditions, two conditions have to be satisfied for you to have a bell-shaped distribution for sample proportions. All right. For you to have bell-shaped distribution for sample proportions. Okay, any questions so far, guys?
No, not yet.
All right, now, how do you find, there is a bit of a kind of involved mathematical / logical derivation behind this. And those materials, I don't know if you have looked at it, I have provided it in the course materials, but that is beyond the scope of this class, okay? That's more advanced topics, but I have provided it in the course materials. If you can fall asleep, you can read it, okay? But basic idea is this, what I just described here. I really love to explain things in a way so that ordinary people can understand it. Like people with no math background can kind of get a feel for it. That's my objective always. Try to explain the mathematical concepts to somebody who is not a professional in that field. That's how you get people motivated, excited, and everything. You know, I'm so curious now that I'm talking about this. I want to give my all-time favorite example to you guys. But before that, let me write down this formula. P hat. So how do you create a confidence interval for population proportion? Remember, I talked about PMS. PMS stands for proportion, mean, and what? Standard deviation. So we are going to do PMS for confidence interval and PMS for hypothesis testing. Now, the S portion, I may or may not do it because it involves something called chi-square distribution. And this course used to be 5 units. However, for whatever reason, they have reduced it to 4 units, which I'm not a big fan of. This is not an easy topic. I want my students to get more hours, contact hours with me than less, but the administration has decided to make it 4 units and reduce the amount of materials a little bit. So, but I still try to cover this if I can manage time. So if I can manage time, I'll do it. If I can't, I won't. So going forward, we will do hypothesis testing for PMS and confidence interval for PMS. I will do confidence interval first and then hypothesis second. So now how do you create confidence interval for proportion? So there is a formula for it. P hat plus or minus Z sub alpha over 2. Z is something you have seen before, right? Times square root of P hat times 1 minus P hat divided by n factorial. Okay.
Mr. Hussein, what is the symbol after the Z? It's something
Alpha.
over 2.
Alpha. Alpha male, alpha female, whatever. Alpha. It's a Greek letter A, I guess. A-L-P-H-A, alpha.
Oh, okay. I was like, wait.
I don't know if they spell it alpha. I don't know. No, not this one. I think this one, alpha.
So, but it's a symbol of an A, right? The letter A.
Yeah, it's not my handwriting is not exactly rocket.
No worries. I just take notes, so I was making sure that I know what I'm writing. So
this is how it looks like. This is how it looks like. Kind of is funny, but sigma is like Greek letter S. So sometimes some students tell me, Mr. Hussain, what is that looks like a fish? Apparently, to some students, this looks like a fish. Sigma. So this is the Greek letter sigma, standard deviation for the population, and this is alpha, which is called significance level.
So is it basically like an infinity symbol with its butt cut off? Is that what I'm seeing?
Yes.
Okay.
Absolutely right. Absolutely right. So that's the formula. And this thing collectively, after the plus minus sign, is called E, or margin of error. So E is for margin of error. Okay. So we'll write something like this. P hat plus or minus E, which is the margin of error. E is equal to Z sub alpha over 2 times square root of P hat times 1 minus P hat, all of it divided by the sample size n. Okay. All right. Now I'm going to give you my favorite example. Anybody has any question about these materials? After that, I'm going to start talking about actual confidence interval creation. Anyone has any question about this material? No question, everybody okay? All right, so I'm gonna give you this interesting example, and it's true. Many years ago, I don't know, maybe 250 years ago or something, there was a little boy. His name was Gauss. It should not be a surprising fact that we are saying Gaussian distribution, okay? His name is Alfred Gauss, German mathematician / physicist. He was a multi-talented guy, extremely talented. And apparently there is a ironic statement about him. In addition to all the great things, his wife was about to die and he was working on a math problem. Somebody came and told him, hey, your wife is very sick, she's gonna die. Then he said, ask her to wait. So that's very interesting.
It's all bad.
But when he was in 5th grade or something like that, for 4th grade, his teacher, I don't know if he was a woman or man, said that, let's say it's a woman, she said that, guys, I have some work to do. Remember, in those days, they don't have calculators. So your job is to do the following: 1 plus 2 plus 3 plus ... plus 98 plus 99 plus 100. Okay. So you need to add all these numbers. 250 years ago or so, what's going to happen? Kids are going to sit down and start adding. So teacher thought she would need half an hour, and by the time she comes back, some students may have the answer. Okay. And she wasn't expecting that anybody would get done with it. So before she could leave, something strange happened. A little boy, he raised his hand and said, hey, I got the answer. He's like, what? You got the answer? And then she checked, and he got the answer. Of course, he didn't use calculator or any of this. Do you know how he did it? He didn't even use a formula. This is my all-time favorite example to give to my students to motivate them. And by the way, that little boy is nobody but Gauss, Alfred Gauss. We talk about the Gaussian distribution, bell-shaped normal distribution. He's the one that came up with the formula that I showed you a while ago. Anyone has a quick thought on this? Okay, since I'm recording it, I don't want to spend too much time on it.
I was gonna say, did he come up with his own kind of shortcut or something?
Yes. So let me show you this thing. 1 plus 100 is what?
101.
Good. 2 plus 99 is what?
101.
3 plus 98 is what?
Same thing, 101.
Do you see the pattern here? And how many such pairs are going to be there? 100 numbers, right? There will be 50 of them, right? So if you multiply it, you're going to get 0, 0, 0, right? Then you're going to get 5, 0, 5, right? Answer is 50, 50. Okay. Does it make sense to you guys?
Yeah, he was a sorcerer, it sounds like.
What is it?
Well, he was a sorcerer, it sounds like.
It's a pure stroke of genius. This is the same boy. I heard that in another case, his father was an accountant, and in those days he was I heard that he was like 3-year-old or something, maybe even older a little bit. His father was doing some accounting stuff on his paper. Imagine, it's not doing accounting stuff right now, like 200, 300 years ago. And the kid was playing in the room, and then the dad is doing the work, and then suddenly the kid said, "Dad, you made a mistake." You'd be surprised, right? Um, and then the mistake was at the bottom of the page, and the number was right here, and he did all these calculations, right, and came up with this final number. And the kid actually looked at all of them and said, "You're wrong." And the kid was correct that he made a mistake. And now let me give you the one of the another examples that was motivated by this. That's also my one of my very favorite examples. There is a wonderful, smart lady. Her name is Miriam Mirzakhani, I think. Mirzakhani, I don't know. I may have misspelled the last name. Miriam Mirzakhani. She was a professor at Stanford, and she's an immigrant from Iran. And when she was little, not so little, I think middle school or something, okay? When she was in middle school, I think 7th, 8th grade, her brother, older brother, actually gave her this example, exact same example. She said it in her biography, that, not biography, in her talk or something, that her brother gave her the exact same example of Gauss's adding these numbers, and that motivated her so much about math that she actually started to work on math, and she got fascinated by it. And that led her to go to Harvard, and she won some big award in the International Math Olympiad. And then she went to Harvard to do her undergrad or PhD in mathematics. Oh, Miriam Mirzakhani, somebody has given me the name Miriam. So that's why. Okay, thank you. Thank you, Jessica, Maryam Mirzak. As it turns out, I spelled the last name properly, but first name I misspelled it. Miriam,
I found that funny too.
Ryam, Miriam Mirzakhani. And the exciting news about her is this. It's a sad story and at the same time a wonderful story. She, Nobel Prize, right? Nobel Prize is the most prestigious award given to people, those who achieve extraordinary success in their specific domain, like physics, chemistry, medicine, etc., etc. Except for Nobel Peace Prize. That one I'm not so sure about, and that's very politicized. Other than that, all the Nobel prizes are given to people who do extraordinary work in their fields. And you can imagine it is given every year. And unfortunately, there is no Nobel Prize for mathematics, but there is something similar in mathematics that's called Fields Prize, I guess, FIELDS, I guess, Fields Prize, Fields Award. This is much more rigorous than Nobel Prize, by the way. It's given not every year, Fields Prize or Fields, it's called actually Fields Medal. I even forget the terminology that they use. Fields Medal is given every 4 years. Not every 1 year, is given every 4 years. Plus, you have to be less than 40. If you are over 40 or 40, you cannot win this award. And she's the first woman ever to win that award. Okay, which is amazing. She's the first woman to ever win that award. And guess what? There was wonderful news, but followed by a tragedy. She passed away from breast cancer. And she was, I think, barely 40 or around 40 when she died. Recently, she died. Okay, that's all. This is my favorite example to share, so I shared it with you. I hope it motivates you. Now, let's get back to our math problem. So we are going to create confidence interval, okay? We are going to use this formula. So let's go ahead and do a few problems. What I'm going to do, I'm going to do 3 problems in a row. Then I'm going to let you work on things, all right? So pay attention what I am doing and you will get it. It's not hard. In order to get an idea about the true population proportion of iPhone users in the US, Apple surveyed 200 randomly selected smartphone users and found that there were 120 that used some version of iPhone. Create a 95% confidence interval for the true population proportion of iPhone users among the smartphone users. Again, wording is heavy. Let me break it down for you in ordinary people's terms. Let's say you want to find out what percentage of the people actually use iPhone. That's all you want to do. So you take a sample and then find what percentage said they use iPhone, and then based on that, you guess, okay, maybe it's a little bit more and a little bit less. Remember that example I gave you? Let's say you found 45% of the people use iPhone from your sample. Then you may say, maybe it's extra 5% that I should add or subtract 5%. So you'd say it could be as low as 45 minus 5, 40%, or as high as 45 plus 5, 50%. So your best guesstimate would be, or estimate would be, between 40 and 50%. Okay, that's what the confidence interval is. Now we are going to do it in a more formal way using the central limit theorem. A couple of things I'm assuming here. Let me write it down. NP is greater than or equal to 10, and Q, or N times 1 minus P, is also greater than or equal to 10. I'm making these assumptions, okay? So you can assume those. Now, let's go ahead and put it together. How many people have you surveyed? That's the sample size. As you read the problem, please collect this information. That's 200 people. How many of them did say that they use iPhone? That's the X. Okay, that's variable. Okay, 120 of them said that they use iPhone. Then what is the p hat, or the sample proportion? Proportion means percentage. So don't be confused by those fancy sounding words. Okay, proportion is percentage. Sometimes I hear words, that sounds so, so academic. But we're trying to talk about ordinary things. One of the great things about politicians is that great politicians, they take an idea and express it in a very simple way so that everybody can understand it, or almost everybody. So if we can take math and kind of like break it down in a simple way so that people can understand it. So percentage, if I say percentage, pretty much everybody understands it. If I say proportion, people will be confused, many people. Okay, so let's go ahead and find the percentage. How do you find the percentage? It's like X over N, which is X is 120 over 200, which is, by the way, 0.6. So your p hat is 0.6. Next, let's go ahead and find something else. Confidence level. What is the confidence level that we want? In this case, we want 95%, but please convert it into decimal 0.95, right? Now, here comes the alpha, infinity without the end, okay? alpha is called significance level, okay? Significance level, okay? So alpha is defined by 1 minus the confidence level, or CL. In this case, alpha is going to be 1 minus 0.95 or 0.05. So your alpha is 0.05. Now I'm going to divide alpha by 2 to get alpha over 2, which is going to be 0.05 divided by 2, which is 0.025. Okay, remember this number, we will need it. So I did everything on the right side to solve the problem. I pretty much had,
quick question.
Yes.
Right there where you wrote significance, above that alpha symbol, what is the symbol you have right there where it says 95%?
Oh, that's not a symbol. That's CL, confidence level.
Oh, okay. I was like, what am I looking at right there? Thank you, though.
Mm-hmm. Maybe I should write a little bit clearly. With these pens, it's hard to write on a soft surface. I heard that there is another tool which I'm thinking of buying. It's like writing on a piece of paper. All right. Okay, now let's go back to our central limit theorem. Remember our central limit theorem? So this is mu sub p hat, sigma sub p hat, okay? I'm not going to write the details. So now you want 95% confidence level. That means 95% of the times you create confidence interval, it will include the actual population parameter, which is just this guy, melting P, okay? So now that means you have to be within the middle 95% or 0.95. If your sample, so this is the sampling distribution, if your sample basically falls between these two, okay, sample proportion falls between these two numbers, you will be including this guy. That's what it means. And what are the chances of that happening? 95%. So 95% chance of including, 95% chance of including this guy, this middle guy, right? That's what our ultimate objective, right? Mu sub p hat is equal to p, right? Proportion. Now, 95% of the times we want to include it, then 10%, I mean 5% of the times we don't, well, not that we don't want to include it, it won't be included, okay? 95% of the times it would be included. Now, this right side and this left side would be the remaining. So if your sample somehow ends up here, it will not include this point. It will not include this point, population parameter. Or if your sample ends up becoming on the right side, sample proportion, then it will not include this population parameter P. So that's the thing. Now you need to find this value, this point. Okay, so 95% in the middle, right? What is outside, guys? What is on this side? And what is on this side?
2.5.
2.5% or 0.025. Thank you. Not 0.05, 0.025. 0.025. That's why I have this 0.025. See, alpha over 2. This alpha over 2, 0.025. Is it okay, guys, everybody? Now, this is the hard part. Not hard, it's like you have to get used to it. This point here is nothing but is z sub alpha over 2, which is the negative. In my case, z sub alpha over 2 is going to be z sub 0.025 because alpha over 2 is 0.025. And this point is going to be your Z sub alpha over 2 again 0.025. 0.025. Okay. So how do we find this? Any suggestion? I will tell you. How do I find this Z value? Can anybody help me out?
Would you look at the chart?
Yes, Don, we will, but what are you looking for? Tell me.
I'm not sure.
Anybody? Anybody wants to join in?
Are you asking what we're looking for in the chart?
Yes, exactly, Monica. What
Would it
am I
be,
looking for? Sorry, go ahead. My
would
apologies.
it be the 025?
What is it?
Would it be the 025? The 0.025?
Yes, 0.025. How do I look for it?
Are you just gonna go to the chart and then match the two numbers that correspond to where it meets? So 0.6, what was it? 0.5987?
Okay. Thanks, Ron. Monica?
Yeah, what Don said.
Okay. Thanks, Monica. Anybody else? Anybody else wants to participate in the conversation? Danny?
I do have a question. If we're gonna find the 0.025, would we look for the negative and the positive one as well?
Probably, yes.
Would we be looking up our the Z chart?
Yeah, that's why you look, because it's the Z. How do you look for it? That's what my question.
Are we using the same chart we're using for the central limit theorem?
Yes, Z score, standard normal distribution table, yes.
Yes, that.
Yeah, but how do you look for it? What are you looking for?
So we would be looking at the top number, not the side number. But okay, never mind. I thought I
No,
had something, but
go ahead. Maybe you do.
The
Go
mu?
ahead.
Would you be,
so instead of going down on the chart, you would look at the top number, the ones that start with 0.0. But I wasn't sure. I'm not sure where we're supposed to go from there.
Okay, all right. Danny, you were saying something.
I wasn't sure we were gonna be going through mu, but never mind.
Okay, I don't mind. Any other volunteer? McDale Ramirez. McDale Ramirez.
Yes.
Okay. Do you want to share your thoughts with us?
Or just go to a 2.5 on both negative and positive.
Okay. Ariana Infante. Ariana. Viviana Infante. Are you guys related or just happen to have the same last name? Ariana, Viviana. Okay. One last time. Anybody? Jessica?
Yeah, sorry, I'm having trouble with my internet, so I'm still kind of catching up on everything.
Okay. All right. Let's go ahead. Yes. Go ahead.
I was gonna say, isn't it when we go like to point 2 and then go over 5? Or am I wrong?
Sorry, I apologize. I couldn't hear you.
He asked like if you go to the z-score chart, find 0.2 and then move over 5 positions and find the corresponding number. is what
Yeah.
she meant.
No, no. I think you guys are missing a crucial point here. What is given here?
The 95%.
Yes, from that we come up with this 0.025. What is 0.025 here? Is it the z value? Or this one? Is it the z value, 0.025? Yes or no?
Possibly, because you have it with right underneath one of these arrows. You have it as z.
Okay, it is not z value, it's the probability. See, the shaded region is 0.025, right? The shaded region is 0.025. That's the probability. In the continuous random variable case, probability is given as an area under the curve, area under the function, right? So you're given probability, not the z-score. Remember, I told you, you need to know what is given and what is it you're looking for. At times, you're given z-score and you're looking for the probability, but at other times, you're given probability, you're looking for the z-score. So if you look it up in the table, you have your z values going down like this and 0.00, 0.01, 0.02, and all the way up to 0.09, right? Then if you have z-score, you kind of look at the first column and then go to the right and stop at the corresponding column on the top, right? To find it. But you're given the area, so you have to look in the body of the table and find the value that is closest to 0.025. Once you find that, you look at the column value, you look at the row value, and you add them. And that is your z-score. So all of you are looking at the wrong thing. You're thinking, oh, I'm going to look at 0.025. No, that is not what you're looking for. You're not looking for the z value. You are not given the z value. You're looking for the z value. So if you're looking at 0.025, by looking at this column, the z column, and then going to 0.05 on the right somewhere here, and then finding the number somewhere right here, that is wrong, because this 0.025 is not the z value. It is the probability. So remember, two very specific things. You are given z value or you are given probability. Which one are you? Which one is it that you are given? Which one of these is that you are given? You've got to figure that out. You are given the probability area. I kind of mentioned it a few times. So please make sure that you're absolutely clear on what is it you're looking for. Okay? It's true like life. If you don't know what is it you're looking for, you'll never go there because you don't know what you want. That's a problem. So all of you are looking for z corresponding probability, whereas you should be looking for probability. You should be looking for z-score. And if you do it, I think Danny gave the number. This is gonna be, oops. This is gonna be equal to negative 1.96, and this is gonna be equal to positive 1.96. Negative 1.96 versus positive 1.96. So now your formula is p hat plus or minus margin of error. And in our case, margin of error is z sub alpha over 2 times square root of p hat times 1 minus p hat, all of it divided by the sample size n. Z sub alpha over 2 is 1.96, all right, times square root of p hat is 0.6, 1 minus p hat is 1 minus 0.6, all of it divided by the sample size, which is 200. So that's going to give you E, or margin of error, 1.96 times square root of 0.6 times 0.4, which is 0.24, by the way, divided by 200. If you do the calculation, I think this is what you will get. 0.24 divided by 200, square root of it, times 1.96, that comes out to be equal to 0.0678. And I'm gonna, by the way, guys, round it. So E is approximately 0.07. Let's round it to the 100th position. So I'm gonna round it here. So your margin of error is 0.07. So your P hat plus or minus E is gonna be equal to P hat is 0.6 plus or minus 0.07, which is to say your confidence interval is going to be 0.60 minus 0.07, comma 0.60 plus 0.07. So 0.60 minus 0.07 is 0.53. Is it right? Yeah. Comma 0.60 plus 0.07 is 0.67, which is the same as 53% to 67%. There you go. 53% to 67%. So your confidence interval is 0.53 to 0.67, which translates to basically 53% to 67%. So based on your calculation, you're saying that true population parameter, true percentage of people that use iPhone falls between 53 and 67% in the US population. True iPhone users fall between 53 and 67%. And how confident are you? You're 95% confident. What does that mean? You expect to be correct 95% of the times, meaning that if you were to create a lot of confidence intervals like this with exact same sample size, it has to be the same sample size. In that case, by the way, about 95% of those intervals will include the actual population proportion or actual percentage, and about 5% of them will not. So if you were to create 1,000 different samples and create 1,000 different confidence intervals from these samples, and then out of that, about 950 of them, approximately 950 of them will include the percentage, population percentage, and approximately 50 of those intervals that you have created will not have percentage. I mean, will not include this population proportion. And those 50 probably came from either to the right or to the left. That means it fell on the left side or on the right side. Only if you fall on the right or extreme left, that's when you will not include. Your arms are not going to stretch up to that far, okay, to reach this point. Now, this 1.96, that's actually kind of like the distance from here to here. You can think of it that way, all right? That kind of If you are sitting in the middle, you are stretching your hand in both directions. So in the right direction, you'll go here. In the left direction, you'll go up to here. But if your mean happens to be proportion in this case happens to be here on the right, you'll not be able to stretch your arms enough to reach or include this point. Or if your proportion is right on the other extreme to the left, you cannot stretch it. 1.96 is not going to take you up to that far. So I have given you lots of explanation on this problem. This is the first problem we are working on. That's why I spent a lot of time on this. And it's very important to spend a lot of time on this. And once you have good understanding of it, it's gonna go by very quickly to others. Now I'm gonna pause here for a second and I'm going to go ahead and ask you. So please tell me, anybody has any question about any part of this problem? Anybody has any question about any part of this problem? Don't hesitate, please. Where did 0.6 come from? 0.6 comes from the information given in the problem. The problem gave you, let me use a different color. Problem gave you sample size 200, and it also told you that out of 200, 120 people said that they used iPhone. So P hat is the sample proportion is X over N. 120 over 200, that gives you 0.6. That's where the 0.6 comes from. There's the proportion of the sample or percentage that you get from the sample. And it'll change to, when we are dealing with mean, it'll change to sample mean. When we are dealing with standard deviation or variance, it's going to change to standard deviation or variance of the sample. Dennis, is it okay? Yeah, okay, good, thank you. Anybody else, anything? Okay, thank you, Jessica, for your comment. And yes, we'll be doing plenty of examples. You cannot miss it. Just be in the class, you'll get it. You have to try hard not to get it. Okay, so just pay attention and we'll be okay. Let's go ahead and jump into the next problem. Cyberbullying is a major problem in today's blah, blah, blah social media. Okay, I made this problem a while ago. So social media has extended beyond Facebook's, Twitter's, Instagram, Snapchat. Now we have to include TikTok. Okay, that's the hot topic nowadays. Pinterest was there and all those things were there. Now, you're curious. So cyberbullying is basically harassment on the internet. Okay, mostly verbal harassment. People experience it on the internet. You're curious about the true population proportion or percentage of social media users that were cyberbullied. So you decided to take a survey of 300 people. So you decided to take a survey of how many people? 300. What is this 300 gonna be in terms of symbol? What symbol is gonna represent 300 here?
N.
Thank you. N is equal to 300. You surveyed 300 people on the social media, asked them whether they have been cyberbullied. 120 responded yes. What symbol should I be using for 120?
X.
Exactly, X is equal to 120. So I have N, I have X. So Dennis, I can find P hat or sample percentage, sample proportion now, which is X over N. 120 over 300. If you do the math, it's 0.4. So your P hat is 0.4. Now let's find the confidence level. This is CL, Don, it's not symbol. What is the confidence level here?
So 90%, 0.90.
90%, which is equal to 0.90. That is 90% confidence level. Okay, so significance level alpha is the significance level. Alpha is always equal to 1 minus the confidence level, which is 1 minus 0.9, which is going to give me alpha is equal to 0.1. But we have to divide it by 2. Alpha over 2 is going to be 0.1 divided by 2, which is 0.05. So alpha over 2 is 0.05. Okay. Now let's go ahead and draw the diagram. Guys, please make sure to draw the diagram. That will help you see things. Now I'm going to draw this diagram. That's the sampling distribution. There's mu sub p hat and sigma sub p hat. Now I want 90% confidence level. So the middle portion is going to be 90% or 0.9. Middle portion is 90% or 0.9. What is the area on the right? And what is the area on the left? There's the alpha over 2, right? Which is what? 0.05 and 0.05. Perfect. Now we need to find this point. That's my negative z sub 0.05. And that's my positive z sub 0.05. Yes, Don?
Where you have 90%, did you write 0.9 below that?
Did I make a mistake? Yeah, 90% is 0.9. Yeah.
Okay, so I was trying to see, because I see a little squiggle. I was like, is that a point? I was trying to make sure it's a point.
It is a point.
Sorry, I'm not trying to criticize your writing. I was just trying to make sure I get my notes correct.
You have the right to criticize because you are the consumer of my writing, right? You have to understand, right?
No, yeah, I understand. I don't want to make you feel like I'm like criticizing your writing or anything.
No, you are welcome to criticize my writing if I'm not writing clearly, so that I can write clearly and you can understand it. It's like the pencil is kind of like weird. I used to use the older iPad, that was much better. With the newer iPad, somehow it just doesn't come out properly. That's why I'm kind of thinking of getting another thing. There is another device out there which is easier to write with. It feels like paper, writing on paper. But I have to buy all these things out with money out of my pocket, right? We are teachers, not exactly billionaires, right?
Yeah, are they expensive, those little tablets?
I spent like almost a good $2,000 to buy this iPad at 1,800 something, iPad and the pencil. I paid that money out of my pocket. The college doesn't give me anything for that.
Oh man.
All right. So now I want everybody to find these values. Go and look at your Z table. Remember, you're looking for probability. You're looking for Z-score given probability. You're looking for Z-score given probability, and the probability is 0.05. I already see somebody got it. Don't look it up in the chat. Look it on the table first. You look at the table, in the body of the table, where you get the closest value to 0.05. There is nothing there really except exactly 0.05. You have 1.05, 05, and you have another 0.0495. And in between there is a star with an arrow, and it goes down and it puts negative 1.645. And that's what it is. So this is a negative 1.645. Great. So this is negative 1.645. This is positive 1.645. And now the rest is easy. Your p hat plus or minus margin of E, and margin of error, not margin of E, plus or minus E, which is equal to Z sub alpha over 2 times square root of p hat times 1 minus p hat all of it divided by the sample size n. My z sub alpha over 2 is 1.645 times square root of p hat is 0.4 times 1 minus 0.4 divided by the sample size n is equal to, what is the sample size? 300. And if I do the math, I get E is equal to 1.645 times square root of, this is going to be 0.24 over 300. And let's do the calculation here. 124 divided by 300 square root of 8 times 1.645 is 0.0465. That's equal to 0.0465. And I'm going to round it to the 100th place. So that's going to be E is equal to 0.05. So your P hat plus or minus E, P hat plus or minus margin of error is going to be 0.4 plus or minus 0.05. So that is going to give you 0.40 minus 0.05, comma 0.40 plus 0.05 is equal to 0.40 minus 0.05 is 0.35, comma 0.40 plus 0.05 is 0.45, which is the same as 35% to what? 45%. So your confidence interval based on your sample is between 0.35 and 0.45, which is between 35% and 45%. How confident are you that the actual percentage of people who are being cyberbullied is about in between 35 and 45%? How confident are you that the actual percentage of people who are being cyberbullied will be between these two numbers, or in this window between 35 and 45%? You are about 90% confident, meaning, again, if you repeated the same experiment many times, let's say 1 million times, about 90% of the times, or 900,000 of them, it will include the actual population parameter, which is proportion or percentage, and about 100,000 of them will not include the population percentage or proportion. And that's how you do this one. Now you probably are feeling a little bit more at ease with this problem. Now let's go ahead and do the next one. Any question on this one before I move on? Anybody?
No, I don't have anything.
Okay. The next one is, you are interested in finding out about the true population proportion of fellow students that plan to attend 4-year colleges or universities after finishing their first 2 years here. Okay. You asked 50 students and found that 200 plans to attend 4-year institutions and create 80% confidence interval for the true population proportion of students that want to attend 4-year institutions. All right, so let me just write down the numbers here. What is your N here, sample size?
50?
50. What is your X here?
20.
20, thank you. What is P hat?
80% or 0.8?
No.
No, sorry, it's the 20 over
40%.
50. My bad.
Fine.
I'm getting ahead of myself.
Okay. P hat is 0.4. Great. And what is confidence level here? 80%, right? which is 0.80 or 0.8. What is significance level alpha, which is 1 minus the confidence level, which is 1 minus 0.8. That is alpha is equal to 0.2. So we need to divide it by 2. Alpha over 2 is equal to 0.2 over 2, which is 0.1. Alpha over 2 is equal to 0.1. All right. Alpha over 2 is equal to 0.1. Next, we need to go back to our sampling distribution. By the way, in all of these processes, I'm kind of assuming NP is greater than or equal to 10 and NQ is greater than or equal to 10, or Q is 1 minus P. And we are going to be kind of relaxed about this condition. We are kind of assuming that it will work out, all right? Now, our sampling distribution. So these two conditions ensure the normality or bell-shapedness, okay, or Gaussian distribution. So that's my sampling distribution for sample proportions. So this is mu sub p hat, and this is sigma sub p hat. All right. Remember, mu sub p hat is equal to p, and sigma sub p hat is equal to square root of p hat times 1 minus p hat, all of it divided by the sample size n. All right. Now let's go ahead and talk about it. What is the middle percentage here? 0.80. What is going to be in the tails? 0.1, exactly, 0.10 or 0.1. Now, what is my z values? Z sub 0.1. Negative z sub 0.1 and positive z sub 0.1. Everybody look it up and give me that number, please. Okay, please unmute yourself and let me know. What number do you get? That is incorrect. Incorrect. Correct. Jessica. Remember, your given probability, you're looking for z-score. So your probability is 0.10. What is the closest value you can get that is close to 0.10? If you look at the table, you'll see it's 1.003, I believe, if I recall correctly. You look at the corresponding z value here and vertically corresponding decimal portion. And that number is negative 1.28. And by symmetry, it is going to be 1.28. So your z sub alpha over 2 is 1.28. Now, p hat plus or minus margin of error. Margin of error is z sub alpha over 2 times square root of p hat times 1 minus p hat, all of it divided by sample size n. So 1.28 times square root of p hat is 0.4 times 1 minus 0.4, all of it divided by sample size 50, which is going to be equal to E is equal to 1.28 times square root of 0.24, because this is going to become 0.24 because 1 minus 0.4 is 0.6 divided by 50. So let's go ahead and do it. 0.24 divided by 50 square root of it times 1.28. It gives you 0.0886. 0.0886, and I'm going to round it to 100 place. E is equal to 0.09. So E is equal to 0.09. So your margin of error is 0.09. So P hat plus or minus E is equal to P hat is 0.4, right? Or 40 plus or minus 0.09. That's gonna give you 0.40 minus 0.09, comma 0.40 plus 0.09. 0.40 minus 0.09 is 0.31. 0.31, comma then 0.40 plus 0.09 is 0.49, which by the way is the same as between 31% and 49%. So your confidence interval for actual percentage of people that want to attend 4-year colleges or universities after 2-year community colleges is between 31 and 49%. Okay, is between 31 and 49%. How confident are you in your calculation? 80% confident, which means that again, once again, if you were to create many samples of the same size of 50, and from each of these samples, you have created a confidence interval like the way we did, about 80% of those will include the population proportion and 20% will not. So if you created 10,000 intervals from 10,000 different samples of size 50, out of 10,000, about 8,000 will not include the population proportion or population percentage. Sorry, about 8,000 will include. Did I say will not? 8,000 will include the population proportion approximately, and 2,000 or 20% of 10,000 will not include the population proportion. That's what it means. Now, one interesting thing I kind of want to touch on here. So this is kind of a big range, 31 to 49, about 18% gap in between, right? What if I want to bring it to, let's say, I don't know, 5-6%, 5 to 6%? Okay, now you have 18% gap between the two. Can you squeeze it in? That means, can you be more precise in your estimation or in your confidence interval creation? If yes, how do you do that? Think about it. And there is a comment here. Let's see. Do you have to plug in the formula with negative 1.28 because you didn't? I don't have to plug in the negative 1.28. Look at this. It has a plus or minus that takes into consideration that. So just put in the positive value.
Mr. Hussein, quick question.
Yeah.
Oh wait, never mind. I answered my question just as I was going to ask you because I looked at the notes. Never mind.
So how do you make? Thank you. How do you squeeze it in, this confidence interval, more closer to each other? What change can you make easily to? If somebody says, "Oh yeah, it's between 80%, 31% and 49%," but I want a better range, maybe I don't know, 40 between 47 and 51, 47 and 53 or something. Or not 47, 39 and 42, something along that line. What can I do? Can I do anything? Anybody?
Should you divide by something? I'm just guessing here.
You will kind of, but I would prefer a more precise response though.
Would you do the mean of both 31 and 49%?
Any other recommendations? Any other recommendations, anybody? Jessica, you tried to say something, I guess. I couldn't hear you.
I didn't say anything.
Oh, I thought you did because that's what the response here was. But do you want to share your idea? How can I bring it closer?
I still don't quite have one. I keep getting kicked out of the class, so
Yeah, I know. I noticed that your internet.
yeah, I apologize. That's my internet.
No. It's not your fault, right? You don't have to worry about it. It's just that technologies. Our internet is quite slow. Let's put it
Yeah.
that way.
I live out in Prunedale too, so I definitely get the slow end of the stick.
Oh, it's not because you live in Prunedale. It's pretty much the entire country. Internet is not as efficient. You should go to some of the Asian countries like South Korea, Japan, and their internet is much better than ours. Even in some of the developing countries, and we pay a lot of money for the internet, yet we get really poor quality service. You should be able to hold a Zoom meeting without much difficulty. And you don't live far away. You are close to a big city. It's not that you live in the middle of nowhere. Okay. Anybody else? One last chance. You guys don't see it? Or Jessica, Lara? Jessica, Lara, any comment?
Would you add them together and then divide by the total number of results?
I think something similar to this was proposed by somebody else. I forgot who it was. Let's see, Pedro, do you wanna share your thoughts how to bring the confidence interval closer, reduce the window?
By reducing it.
I want to reduce it. How do I do that? All right, I gave you plenty of opportunities. Let me just do it. What if I took a sample of size 500 instead of 50? What's going to happen? Everything else is the same. I take a sample of size 500, and let's assume that out of 500, 200 said, oh, okay, we are going to go to college for a year. That keeps the p hat at 4. So then what happens? Only thing changes is your margin of error. E is equal to 1.28 times square root of 0.24 divided by, instead of 50, now you're dividing by 500. What does that give me? 0.24 divided by 500 is equal to this to the power 0.5 times 1.28. That is equal to 0.0280. If I round it, it becomes 0.03. So your margin of error is 0.03. So p hat plus or minus e is equal to p hat, which is 0.40 plus or minus 0.03 e, which is going to give you 0.40 minus 0.03, comma 0.40 plus 0.03. 0.40 minus 0.03 is 0.37, comma 0.40 plus 0.03 is 0.43. Do you see? This is between what? 37%, 37% and what? 43%, much closer, right? Do you see the difference between this and that? They're much closer. Now, if you want to get even more, compact interval, you just change the sample size. Why is it the case? Can somebody give me the intuitive explanation for it? Let's say instead of 500, if I take 5,000, okay? I could do that, 5,000 students, a sample of 5,000. And let's say everything else is the same. Out of 5,000, 2,000 said that they're gonna go to Fourier school. So P hat is 400, 0.40. In that case, this window is gonna be even smaller. Intuitively, why is that the case? Can anybody explain that to me? That's the last question for the day.
I think you told us this a couple of classes back, but I think you said that like when there's like more people, like in this like 5,000, when like the number gets bigger, like it goes like towards like 0.5, which is like half of the like half of people would just like go 4 years and half would be like 2 years. I think it's something like that. I don't know how to explain it well, but I think it was like something like that.
Okay, good. Was it Dennis?
Yes.
Okay, thank you, Dennis. Anybody else? Jessica, the bigger the sample size, the more accurate your answer becomes, the smaller window. Yes, it is correct. The bigger the sample size, Jessica, the more accurate your calculations become. But why though? What causes you to have a smaller window of interval? Anyone?
Totally stumped right there.
Totally stumped. George Lopez. George. Monica.
Yeah, I don't know if I'm being honest.
All right. That's okay. It's good. It's okay not to know, but participate. Give your thoughts. Throw something out. That's the thing I'm looking for. It's not a bad thing by any means to think of something and share your thoughts with us, as opposed to being quiet and not saying anything. So anything, anybody? One last chance before I give out the answer. All right. See, what happens if this n increases, given that your p hat stays constant? If you have a number, let's say the top number is, let's say 0.24, right? Instead of dividing it by 50, now you're dividing it by 5,000. What happens? This number becomes what? What happens to this number compared to this? What happens to this compared to that one? It becomes what? Smaller, right? Which means standard deviation decreases. That means the sampling distribution becomes more narrower. That means your window becomes narrower. That's what it is. Standard deviation changes and the data points become closer and closer and closer to the true proportion. And that is all for the day, guys. Thanks a bunch. Stay safe, stay healthy. I hear that COVID numbers are going up again in California. So please do social distancing, wear mask, use hand sanitizer. And I hope everybody is vaccinated. If you are not, please go ahead and get vaccinated. Save yourself and save others' lives as well. Thank you so very much. Have a wonderful evening. Take care.
Thank you, Professor.
Thank you.
Thank you. Bye.
Bye.